Good afternoon, everyone. It's my pleasure to introduce today's colloquium speaker, Dr. Susan Nossal of the Department of Physics here on the UW campus. Dr. Nossal, a UW Badger, in the sense that she earned her master's and PhD degrees here in 1990 and 1994, respectively. And she was also a postdoctoral research associate with Professor Hitchman from 1996 through 1999. I think it was shortly after I arrived on campus I first interacted with Dr. Nossal, Susan. Her research interests focus primarily on applications of optical spectroscopy and atomic physics to study the solar terrestrial interactions, natural variability, and climatic change in the upper atmosphere. She also has a considerable deep interest in undergraduate education, including using inclusive practices to create supportive learning environments for diverse student groups, incorporating active teaching methods to stress conceptual understanding, training undergraduate peer tutors and graduate students in inclusive and active teaching practices, and sharing information with students and the public about scientific background who are some numerous environmental challenges, particularly climate change. Today's talk is going to be on the research aspect of things, but if you really have an interest in learning more about the types of things she does with regard to undergraduate education, I'm sure she'd love to talk with you about that. But our talk today, solar, cyclic, and climatic influences on hydrogen at the top of the atmosphere. I'm looking forward to that talk. Welcome, Susan.
Oh, thank you so much. Can people hear me? Okay, great. Thank you so much for coming. Thanks for the opportunity to be here today and to share with you some of the work being done in the middle and upper atmosphere to investigate climate change and natural variability in this region. And actually, there have been observed and predicted and observed impacts going all the way up to 400 kilometers in the Earth's altitude, the Earth's atmosphere. As we'll see in a moment, some of these impacts are of larger magnitude, maybe not larger importance, but larger magnitude than in the troposphere. So I will be focusing today on work being done to investigate solar, cyclic, and climatic influences on hydrogen at the top of the atmosphere. And hydrogen is a byproduct of methane and water vapor below. Many people contributed to this work, and I'll just mention a few of them here. Edwin Merkowitz, who got his PhD in AOS, and we're excited because he's going to be bringing an observatory. His plan is to bring an observatory back to Wisconsin. He's now at Embry-Riddle University in Florida. He's in the process of bringing an observatory back to the Pine Bluff Observatory this summer. And then also wanted to mention my pleasure working with Nikon and Ariana, two students doing senior thesis projects related to this work. And then Carrie Woodward from UW-Fond du Lac and Grant Petty and I have been working on trying to understand how the tropospheric scattering impacts on the observations. Also want to thank many colleagues from the National Center for Atmospheric Research because the modeling portions of this work have been done in collaboration with these colleagues. And very interested in feedback from you all too about how our communities can work more closely together. So thanks so much. So some of the research questions that we're addressing or seeking to address are what are the solar, cyclic, and climatic influences on lower to upper atmospheric coupling of constituents containing hydrogen. And in terms of natural variability, the 11-year solar cycle is a major source of natural variability in the upper atmosphere. Also, to what extent might thermospheric hydrogen observations and model simulations contribute to whole atmosphere understanding of hydrogen-containing species and potentially serve as diagnostics of climate change processes. So what I plan to do today is to start with a brief overview of some of the whole atmosphere studies of climate change processes, including some of the seminal papers in this field. Then talk about our hydrogen emission data set that now spans multiple solar cycles. So in terms of upper atmospheric data set, it's a bit on the longer side, but certainly for the troposphere, a short data set. But we'll then also talk about model simulations of hydrogen sensitivity to greenhouse gases and solar variability, and talk about an interpretation of the observations in the context of these simulations, and then end with some comments on future studies and conclusions. So first, to start with some of the overview. So I wanted to just talk briefly about different regions in the atmosphere and the middle and upper atmosphere, just as the temperature cools as they go up into the troposphere. This is illustration showing different regions in the atmosphere, and they're defined according to their temperature structure. So there's warming in the stratosphere. The contributing factor is the ozone absorption of ultraviolet light from the sun. Then cooling in the mesosphere up to the top of the mesosphere, which is where the coldest place in the Earth's atmosphere occurs, or the mesopause, where temperatures on the order of almost minus 100 degrees Celsius. And then in the thermosphere, there's great warming due to absorption of ultraviolet light from the sun, also high energy particles from the sun, heating in this region, and a couple of other processes. In the thermosphere, while the temperatures are very hot, if you were in the thermosphere, you wouldn't feel like a sensation of being warm, but because the densities are so low, but we can think about the temperature as related to the kinetic energy of the molecules. And then in the exosphere, which we'll discuss as well, the exosphere is a region in which the densities are so low that the mean free path of the particle is equal to the scale height, or I should say the scale height is equal to the mean free path of the particles in this region. And talk more about that in a moment. But I guess I'll say here that particles, as a result, can go along orbital trajectories. And as we'll see in a moment, temperatures in the middle and upper atmosphere are expected to cool due to increases in greenhouse gases, and also there are associated changes in composition. And I'm going to talk a little bit in the next couple slides about some of the seminal studies looking at the impact of climate change on temperature structure in the atmosphere, and also, these studies initially will be focused on modeling. So I wanted to mention just a couple of the two models that we'll first talk about. One of them is the National Center for Atmospheric Research's, or NCAR's, single column version of the thermosphere and ionosphere electrodynamics general circulation model. This is a one-dimensional version of a middle and upper atmospheric model, and what I'll first talk about is some studies that extended from the mesosphere up through the upper thermosphere. Secondly, I'll talk about studies with the NCAR whole atmosphere community climate model extended, and there have been a number of talks here in AOS that have included discussion of WACM, or whole atmosphere community climate model simulations. This is actually a model that goes above WACM, so it goes up into the thermosphere and it includes an ionosphere. So it's part of the NCAR community Earth system model, and it models the entire atmosphere up to about 500 kilometers, includes the ionosphere, and it's built on the whole atmosphere community climate model, which in turn is built on the NCAR community atmosphere model. So it's a self-consistent model that goes from the surface all the way up to the top of the atmosphere. So this is probably the first, or the seminal paper that first studied the impacts of climate change on the middle and upper atmosphere. This is by Ray Roble, and also by Bob Dickinson, who was just honored, as I understand, at the last AMS meeting, for probably very broad work. But this, he and Ray Roble ran this single column version of the NCAR middle and upper atmosphere model. And what they did is they ran simulations. So with these were not historic ones, but simulations. So to try to understand mechanisms, to try to understand basic properties of what might happen. And what they did is they both halved carbon dioxide and methane, and they also doubled carbon dioxide and methane. So the solid black curves are the doubling scenario, the dashed curves are the halving scenarios. And what we can see here is that the temperature is predicted to cool in the upper atmosphere, and also predicted to be a decrease in densities. in the upper atmosphere, as with the cooling, the atmosphere contracts. So the atmosphere contracts, leaving a less dense upper thermosphere. Do you have a question?
Yeah, so this doubling and halving of CO2
Yeah, and methane.
and methane was done at where in the atmosphere?
Oh, good question. I would need to get back to you, Mike. When we also ran studies, what we did is with the updated version, what we did is we estimated the amount of water vapor in the middle atmosphere that would have arisen due to methane. So because, but I'd have to get back to you on exactly how the lower boundary was done. Yeah, thank you. Because, which is the advantage of the Wacom-X model, the whole self-consistent model, because then you don't have to make these estimates of the lower boundary. You can actually use lower boundary surface conditions. Thank you. These constituents were predicted to decrease in density. However, hydrogen was predicted to increase, and at the time was attributed to methane increases. So this is these are studies with this is a more recent paper work with the whole atmosphere community climate model extended, and I'll go through this in a bit of detail. This is now showing the temperature structure of the atmosphere predictions when you have a self-consistent model that goes from the surface all the way up to the upper atmosphere. And so what Stan Solomon and his colleagues did is they ran 5 years of runs for the early 1970s, 5 years of runs for the early 2000s, and what they did is they took an average of the temperature in the early 1970s, these first 5 years in the early 70s, and they compared all of the temperature simulations to that average, the average of the temperature in the from these 5 years. And these were semi-historical simulations in that these simulations were run with accurate greenhouse gas concentrations at the lower boundary. However, they ran the simulations for a what they call perpetual solar cycle conditions. So I believe these were from the solar minimum condition to help to try to separate out effects from the solar cycle from that due to greenhouse gases. So what we see here is that we see that there's warming in the troposphere. Warming in the troposphere, cooling in the middle atmosphere, less cooling at the mesopause, and then cooling of larger magnitude in the thermosphere, such that the thermosphere cooling is of larger magnitude and larger percent change than in other regions. And I thought I might also say a little bit about the axes here too. This is, the model is run on pressure surfaces, constant pressure surfaces. So this is an approximate altitude scale. It's not a linear altitude scale. And this is temperature difference from the average of these 5 years. And now I want to share just a bit about the mechanisms as I understand them. So part of the reason we see this structure, which you wouldn't see if it was just due to sun's output, so this is like consistent with a signature from carbon dioxide, how carbon dioxide affects the atmosphere. So carbon dioxide can both emit and absorb and emit in the infrared part of the spectrum. And in the dense troposphere, the dominant process is absorption of infrared radiation by carbon dioxide and producing heating in this region. As you go into the middle and upper, into the stratosphere, mesosphere, and lower thermosphere, what happens is that the dominant process is that carbon dioxide would, it's most likely that a photon emitted by an excited carbon dioxide molecule would escape to space before being absorbed by another molecule or redirected back to the Earth's surface. So this excitation can happen via collisions between molecules. I think probably also from absorption of an infrared photon. So it's a cooling process that it's most likely that the photon will escape to space, causing cooling. There's other molecules in the region that also cause cooling. In the thermosphere, however, where you don't have carbon dioxide, one of the dominant process is conduction that's causing this cooling. So in the mesosphere and lower thermosphere, as the temperature cools, that causes a bigger temperature difference or gradient between the thermosphere and the mesosphere, and in the lower thermosphere, and that causes a greater amount of conduction of thermal energy from the thermosphere down to lower altitudes. So that is the process contributing to cooling in this region. In this region, my understanding is that the mesopause region is still an active area. It's a very active area of research. There's still not the reduction in cooling is seen in both observations and model predictions, and the cause is not completely understood, but maybe due to a dominance of dynamical processes affecting the temperature in that region. Any questions before I move on? Yeah, Dan?
Are ozone changes included in these as well?
Oh, in this model?
Yeah.
I think very likely so. I'd have to get back to you to absolutely confirm, but I'm almost sure that's the case. But I have to get back to you. Thank you. Also, what's important in the upper atmosphere in terms of natural variability is understanding the 11-year solar cycle and the impact of the 11-year solar cycle. So for the 11-year solar cycle, the 11-year solar cycle, the 11-year solar cycle primarily impacts the ultraviolet part of the spectrum in terms of the solar spectrum. So it has especially large impact in the middle and well, especially the upper atmosphere, also the middle atmosphere, as these are the regions that are absorbing in the ultraviolet part of the spectrum. Also to note is that it's approximately 11-year cycle. The strength of the cycle can vary from cycle to cycle. Oh, I meant to say, I think I earlier said that as the atmosphere cools, as the atmosphere is cooling, that's causing a contraction of the atmosphere, and as the atmosphere contracts, the densities in the thermosphere have been predicted to decline. And there have been observations that have been consistent with this decline in density. So this is probably then a main observational data set, I would say, that one of the principal observational data sets pointing to climate change impacts in the highest regions of the atmosphere. And this is work done by John Emmerich, and what he did is, or what he is doing, I should say, is he's analyzing the orbits of many satellites. And so these satellites, over time, their orbits are linked to, or related to the drag properties of the atmosphere. And so from understanding the changes in the orbits of the satellites, you can infer a thermospheric density. And what he's seen over time is a overall decrease in density in the thermosphere. But there's also a solar cycle modulation to that density. And this very low density is likely correlated with a very low or very quiet sun during that solar minimum period. Okay, so next I wanted to move to talking about hydrogen, the work we're doing with hydrogen, and share a little bit about coupling of hydrogen-containing species between different altitudes. So in the troposphere, methane has been overall increasing due to various different processes. And methane actually becomes a major source of the hydrogen-containing species in the water in the middle atmosphere. And this is because at the very top of the troposphere, at the cold tropopause, much of the water vapor is frozen out and is not able to make it up into the stratosphere. But highly convective storms, energetic storms, can bring some water vapor into the stratosphere. I'd love to hear more about that and learn from people doing that kind of work. So as a result, methane can pass from the troposphere into the stratosphere, and it's dissociated through chemical reactions and catalysis reactions into other hydrogen-containing species, including water vapor, molecular hydrogen, also formaldehyde, CH2O. There have been studies with the SABRE instrument. It's an instrument on upper atmosphere satellite, the TIME satellite. SABRE instrument, very recent studies coming out showing increases in water vapor content in the stratosphere and mesosphere. I'll mention the reference in a moment. Another way of studying another parameter that's being used to try to study climate in this region is noctilucent clouds, which occur in the high mesosphere, the whole part of the mesosphere. And there have been predictions and observations showing noctilucent cloud signature, a recent study also showing noctilucent cloud signature that is correlated with increases in methane. But then, if we go up to the high thermosphere and exosphere, these species are broken down eventually into atomic hydrogen, and atomic hydrogen is predicted to increase due to increases in, it turns out we'll see both to methane and to carbon dioxide cooling in the atmosphere. And this is a picture that is of the sun scattering off of hydrogen around the Earth's atmosphere. Also, as I said, carbon dioxide cooling has an impact on hydrogen, and in order to interpret observations, we also have to understand the natural variability due to the solar cycle. And in the exosphere, because of the low densities, the particles, hydrogen can go on long orbital trajectories. So the atoms can go on ballistic trajectories, escape trajectories. Some atoms can transit in satellite trajectories around the Earth. Okay. So next I was going to turn to talking about observational data set and some of the strategies that we used also to try to merge data from a couple of instruments, similar instruments, but still different instruments. And the variability that these data show over multiple time scales. And just ask a few questions too, please. But before talking about the observations, I just want to put them in context with how the different kinds of observations that are being made to understand hydrogen. So there's Fabric-Pro interferometers, which is what I'll be focusing on. And these observations have been made from mid-latitude, from both the Kitt Peak Observatory and the Wisconsin Pine Bluff Observatory near Cross Plains, and I'll be focusing on these observations. There have also been some observations earlier from the Arecibo Observatory in Puerto Rico, and also there are some observations being made in Turkey as well. The TIME satellite, there are measurements being made by the UV instrument of thermospheric hydrogen, SABRE instrument by mesospheric hydrogen, and SABRE water vapor measurements that I just spoke of. There's also efforts now underway to make in situ measurements of hydrogen using CubeSats, very small satellites. This is the ExaCube, and there have been other satellites. This one, unfortunately, talk about that later. There was a problem with the antenna deployment, but there's also Dillinger and ExaCube 2. These are satellites that are based on mass spectrometers for instrumentation. And then there's first light results recently from a transmitting spatial heterodyne spectrometer, and also we'll be mentioning later, excited about working hopefully with Brad on applying this technology to tropospheric measurements of methane and carbon dioxide. But today I'll focus on the Fabric-Pro and mention a bit about how the measurements are made and the instrumentation. So this is a Fabric-Pro spectrometer. The core of the spectrometer are etalons, and etalons are very flat plates of glass, and light can reflect multiple times between the plates of glass and you have multiple multiple reflections between the plates of glass, and thereby producing a very narrow band interference, because you have multiple lines interfering, multiple passes interfering with one another. So you're able to produce a very narrow, high resolution measurement. And also because the Fabry Pro is a pretty big, relatively big collecting area, you can this instrument is able to have a high throughput and high resolution at the same time. And that's particularly important for very diffuse sources, very faint sources, such as the emissions that are coming from these hydrogen atoms that we're looking at for the remote sensing observations. Yeah.
So are these plates fixed so that you're getting just one very narrow measurement, or do they move so that you scan a spectrum?
Oh, very good question. So earlier measurements, the plates were fixed, but you would have a very small changes in the index of refraction of the gas between the plates by slightly changing the pressure between the plates. And that was a scanning technology because at that time the detection was through photomultiplier detection. Now the technology that's used is CCD, charge coupled device camera. So you can actually, the word is not map, but you can display the whole interference pattern onto the CCD chip and then analyze it through an annular summing process. And some of the observations are taken one method, the other with another method. Thanks for the question. So, and we're observing the red line, the 6563 angstrom line in the visible part of the spectrum. This is actually a collaboration also with astronomers. This is the Wisconsin H-alpha map, or Fabry-Perot, and it's been used primarily to study, or its main initial purpose was to study the hydrogen emissions from gas in the interstellar medium, so from atoms in the interstellar medium. The observations are actually made only under very clear skies, only at night, and only when the moon is not present, because even reflected sunlight off of the moon will interfere with the observations. So this is not representative observations, but the light, one of my colleagues did a calculation indicating that the intensity of the light, or the brightness, is about that would be equivalent to taking a small LED and shining it, looking at the brightness 1 football field away from the LED. So very, very faint, looking at the brightness on a screen 1 football field away from the LED, so very, very faint light. You're actually, with the photomultiplier that Brad just mentioned, you're actually counting photons. In the observations, you can have a terrestrial part of the emission and also galactic emission, unless you put the instrument in a location in which there's very little galactic emission. And now that we have the galactic map, we better know where those regions are. So those regions have been some that have been observed, and the observations I'll be showing now will be those that were taken with the regions pointed for very low galactic emission regions. So have to separate these two from one another. Okay, just one more slide about the observations and how they're made. So the observation, the Balmer alpha emission is a solar excited emission, and this shows the energy level diagram for hydrogen. So it's a solar excited emission, so it's excited by predominantly by the Lyman beta line in the emitted from the sun, in the ultraviolet part of the spectrum. So it excites the electron in the hydrogen atom from the n=1 to the n=3 level. And then about 10% of the time, the electron falls back to the n=2 level along these paths and producing the Balmer alpha emission. Because it's a solar excited emission, we can use the Earth's shadow to determine from approximately where the emissions are coming from. So this is a figure which shows this is where this would be the sun and solar line and beta radiation. This is the Earth, and behind the Earth there's a shadow. So the solar line and beta radiation excites hydrogen above the Earth's shadow, and to first approximation, to first approximation, if we're looking in a particular observing direction, most of the emission will be coming from a column that's in the excited part of the atmosphere above the shadow. There is some multiple scattering that also has to be taken into account, but for the most part, most of the emission is coming from a column from above the Earth's shadow. And because the densities decrease so rapidly, most of the emission will actually be coming from just at the location, just above the location in which the observing direction intersects the Earth's shadow. Additionally, I want to now explain the shadow altitude, because it's the viewing geometry has a dominant effect on the intensity, and so the viewing geometry has to be understood in order to interpret the observation. So if we're an observer, this is the observational line of sight, and again, photons are being collected along along the column, mainly above the location in which it intersects the shadow. The shadow altitude is defined as the perpendicular distance from the Earth to the location at which the observing direction intersects the Earth's shadow. Any questions before I go on to showing the results? Yeah, John?
Just a small one. This instrument is used just west of Madison?
There were measurements made just west of Madison, right in Pine Bluff, Wisconsin, right near Cross Plains for many years.
Right.
Then some of the etalons were put into another instrument, the Wisconsin H-alpha macrofabric probe. That was then brought to Kitt Peak Observatory, where the sky conditions are better. And so there were about solar cycles worth of measurements made from Kitt Peak. Then the instrument moved to Cerro Tololo, Chile, where it is currently making measurements of the galactic emissions and the Earth's terrestrial emissions from the southern hemisphere. Then some of the instruments were taken to Florida with Ed, and they're coming back now this summer. So that's sort of the...
I just thought that contamination would be a huge issue.
You mean like from the...
Radiation.
From cities, you mean?
Yeah.
The light radiation? Yeah. So we have a very narrow band filter in front of the etalons also, so that does help. But the Kitt Peak and the Cerro Tololo sites are more pristine, and also farther away from light contamination. But there is a very narrow band filter in front of the fabric row, and the fabric row also acts as produces a very, enables emission in a very narrow band spectral range. Thank you. Okay, so next I wanted to talk about some of the measurement results, and then talk a little bit about the models. So these are, this is a graph showing shadow altitude versus intensity. And this one could say here, one way that helps me in thinking about the shadow altitude is to think about if we were to look into the zenith, make a measurement just straight up. At twilight, you'd be looking through a larger part of the atmosphere and through lower altitude regions that have a higher density. And so you'd expect the intensity to be higher. If you're looking more toward midnight, you would see the areas that would be illuminated would be the higher altitude regions and producing fainter light. And this is what we do see here. This is shadow height versus intensity. The intensity is very faint, only a few Rayleighs. And this is a study in which we look at solar variability, and we're only here taking a very subset of the measurements that were taken pointed in regions of the sky in which the galactic emission is very low. But these are in agreement with other pointing directions. So these were taken during the winter, and these were taken during solar minimum period, and these were during solar maximum period. And as we can see, there's a statistically significant solar cycle variation where the impact on the emissions with higher emissions seen during solar maximum period. And Econ is now looking to compare the solar cycle variation in the winter with that in the summer. So also I wanted to say here that these represent actually spectra, a subset of them in these particular pointing directions, but from multiple nights. And there's a lot of consistency from night to night in terms of the emission if you look within a 2-week observing period. So within an observing period when the moon is not visible in the sky, you'll see a lot of consistency from night to night. And this will be important when we think about the longer timeline, timeline data set in order to interpret those measurements. Also, I'm not going to go into detail in this plot because of time, but just wanted to mention there's also a dusk-dawn asymmetry. These are also shadow altitude versus intensity, where if you look at these are done by Maggie and using measurements from the edge from time block in Berkowitz. But these are looking at the twilight measurements. This part of the measurement is at twilight, looking at twilight measurements during the dawn versus twilight measurements during the dusk period of time. And you can see a separation. So this is an effect that also has to be taken into account in terms of interpretation of a longer timeline data set. Additionally, something to note is that the sensitivity of the measurements are such that they can be used for model comparison, model validation. And also there's a seasonal effect because this asymmetry between the dawn and the dusk is greater during winter conditions than during the equinoxes, with the smallest variation seen in the summertime. And now I just wanted to share just a little bit more, moving into talking about our longer timeline data set. These were again from the Pitt Peak Observatory with Wisconsin H-alpha mapper, also affectionately known as WAM. So the WAM instrument showing the solar cycle variation. If we looked at the comparison of 3 solar minima periods, we see quite a bit of agreement within uncertainties, and I'll talk more about uncertainties in a moment. However, when we looked at 2 solar maximum periods, this was a solar maximum period from the early 1990s. This one was from 2000, 2001. There was a significant difference. And we wondered, well, is this due to the fact, an artifact of the calibration or the data analysis, instrumentation, or is it geophysical? And that's what we spent a lot of time addressing. So is the observed increase geophysical or artifact of the observational strategy, calibration, or data analysis? How can we quantify uncertainties in these and future data sets? And if geophysical, how do we understand the measurements in the context of model simulations? And I want to mention here that these measurements were made with the scanning instrument from Pine Bluff, Wisconsin. The blue measurements were made with the updated instrument, also a higher resolution instrument, also from Wisconsin, and the red from Pitt Peak, Arizona. And the blue and the red measurements are from the same observing period, but from 2 mid-latitude observatories, and they show considerable agreement with one another. So because of time, I won't go into detail with the reanalysis strategy, but we did have the original spectra from the 1990s. So we refit these spectra We redid the calibration. We actually recalibrated a secondary calibration source. Our colleague from astronomy, who is emeritus, Ron Reynolds, he kind of came out of retirement to help us with this. And then we tried to corroborate the calibration in multiple different ways. We also worked with Grant Petty and Kerry Woodward to assess, to apply one of Grant's scattering codes, to couple that with a code that, couple that to a code that provided a hydrogen source to help us assess differences in tropospheric scattering and the uncertainty in the measurements due to tropospheric scattering. But I won't go into more details now unless people would like to know more. Although to say that the calibration is done, the intensity calibration is very important for this interpretation of these measurements, and the intensity calibration is done by comparing the intensity of the atmospheric line with the intensity of a nebular source, a particular region of the nebular source. And our primary source is the North American nebula. Looks like a North American nebula. So again, this is kind of a synergy, a collaboration with astronomy, because the astronomers are able to help determine what are some of the best sources to use. In the end, we found that the calibration could not fully explain the increase. There's still uncertainty in the absolute intensity calibration. We estimate that uncertainty by plotting these intensities using multiple different ways of assessing the calibration. These are different, these curves represent different ways of assessing the calibration. After the intensity calibration, we do still see an increase in both cases, however. Also, we looked at the galactic emission, the tropospheric scattering, went through the log notes to look at weather conditions, and we could not account for this increase due to observational strategy or calibration. So believe that it may be geophysical, although there is a caveat that it's a limited data set, so more data would be necessary to try to see whether this kind of increase is seen during other time periods. So this was, this plot was plotting shadow altitude versus intensity for, these are the early 1990s, and these were the early 2000s, the two solar maximum periods. Now in the next plot, what we'll see is we're going to take one particular shadow altitude, and we're going to plot it versus year to create a longer timeline data set. And that shadow altitude is at a mid-range shadow altitude beyond the region in which the dawn-dusk asymmetry is most prevalent. So this is the Northern Hemisphere data set. This is year, and this is the intensity at a mid-range shadow altitude. And in the past, we treated these data as two separate data sets, where those to the left were one data set, which also showed a solar cyclic signal. And those to the right were a separate data set, because these were taken from Wisconsin. These were taken from Wisconsin, these from Kitt Peak. But we did see considerable agreement between the Kitt Peak and the Wisconsin observations during the same observing period. So we did plot these on the same plot. And now we're in the process of merging them by doing the reanalysis of the 1990s observations. And through the reanalysis, we just completed the reanalysis of 1990s observations. Let me just step back, sorry, I got ahead of myself. Just to say that each of these data points represents many spectra, and in most cases, multiple nights of observations. They were taken during winter months, only the winter months, and they were taken during half-year bins spanning the winter months. I also wanted to mention that here, so this is the axis for intensity. These are the observations. This is F10.7 index. So this is a proxy for solar activity. So a couple things I want to mention here are that this solar maximum period was of greater strength than was this solar maximum period. So given the fact that in the previous emission, given the fact that in the previous studies with the WAM instrument, we see higher intensities during higher solar activity, we might expect that these emissions actually would be higher than these emissions, rather than lower than these emissions. So that's perplexing. The error bars are a compilation of errors that are in the relative errors associated with comparing data from one point with another point. So it's a relative intensity comparison, taking into account the factors I just mentioned. And then the purple and the blue represent the uncertainty and the absolute intensity calibration. So again, so then this instrument is now in Chile. It's almost completed a solar cycle worth of observations from the southern hemisphere, so we're looking forward to now analyzing the southern hemisphere observations. Then when Ed brings his instrument back to Wisconsin, we'll have the potential to do interhemispheric comparisons between the southern hemisphere and the northern hemisphere. So the data suggests that an increase that has not been accounted for by uncertainties due to experimental factors between these two solar maximum periods. And again, we would have predicted that based on past observations that the intensities might actually have been higher with the earlier solar maximum period. And this is the observatory that Ed is bringing back to Wisconsin, and it also will include an SHS instrument. Okay, so now I wanted to talk briefly about some model simulations of hydrogen sensitivity to solar variability in greenhouse gases, and then talk about the interpretation of the observations in this context. I'll now be talking about a updated version of the global mean model that was run for the seminal climate study. But this one now extends down to 30 kilometers. Also, again, the whole atmosphere community climate model extended. And so what we decided to do, what we did here was we wanted to look more closely at mechanisms with this single column model, global average model. So I wanted to try to better understand mechanisms, try to better understand what was the impact of cooling versus changes to the source species from methane. And also, how did the solar cycle affect the predicted densities? So what we have here is, I won't be able to go into detail with the time we have into all the plots, but I will just share a few points from these plots. What we have here is the hydrogen number density on a linear scale and altitude. And this is in the thermospheric region. The solid curves represent the base case scenarios. And we did, this study was also to understand mechanisms, so not a historical study. So we doubled carbon dioxide and methane, and we certainly hope we never get to double carbon dioxide. So it was just a mechanism study. And then the dotted lines represent the hydrogen densities when we double carbon dioxide and methane, and when we double, when we double carbon dioxide and methane at solar maximum and at solar minimum conditions. What the study concluded was, just step back here too. This is, in this plot, we separately look at carbon dioxide doubling, methane doubling, and doubling the two together at solar maximum and at solar minimum. And I'm just going to focus here in the upper thermosphere. In the upper thermosphere, we do see that both carbon dioxide cooling and changes to the source species, augmentation of the source species for hydrogen from methane increases, both contributed to the total increase in hydrogen. But that the contribution from carbon dioxide cooling is greater at solar minimum. And this is thought to be due to the greater effect that carbon dioxide plays in terms of the overall cooling of the thermosphere at solar minimum, whereas NO, my understanding, has a greater effect. NO cooling has a greater effect at maximum than at minimum. So I'm going through this a little fast. But a couple points to note, though, is that both carbon dioxide cooling as well as methane both lead to predicted increases in hydrogen. The increase in hydrogen density due to greenhouse gas doubling was predicted to be higher at solar minimum, which we saw the bigger change, which may not at all be due to greenhouse gases, but we saw the bigger change at maximum rather than minimum in the observation. And that the hydrogen response depends on the phase of the solar cycle. And additionally, that the effect of the solar cycle is a dominant factor. Because this was not a study that was looking at historical values, but a study that was looking at the doubling scenarios. Over the time period of one solar cycle, you'd expect just there have been only few percent changes in the greenhouse gas concentrations in the atmosphere. And as Michael mentioned earlier, one of the limitations is that you have to estimate what the impact would be at the lower boundary of the model due to the doubling of methane and carbon dioxide. So this is preliminary. This is a preliminary result from using the WACMX model, the self-consistent model throughout the whole atmosphere to look at predicted changes to hydrogen throughout the atmosphere, using historical values of greenhouse gases now. And this is over a 30-year period of time, not the same 30-year period of time as the observation, but a 30-year period of time, somewhat close. What's done here is we take a percent difference from an average value we take the average value of hydrogen density from the early 1970s, and then we take a percent difference, calculate a percent difference from that average value. And so what we're doing here is we're looking at the changes, the percent difference changes from the early 2000s compared with the early 1970s. So the percent difference meaning taking the later hydrogen value and comparing it with the earlier one in terms of the percent difference divided by the earlier density. And what we see in the upper thermosphere is that the predicted change is about 8% or so in the upper thermospheric hydrogen over this 30-year period of time. We could talk about other features, but if people have questions about those later. This is likely due, I'm thinking of need to do more investigation of this, likely due to very low densities of hydrogen in this region. So one thing that I'm interested in doing is looking at other species that are containing hydrogen, looking at multiple different altitude regions and trying to understand where in the atmosphere, where it might be more sensitive to climate impacts. And could these potentially serve as additional fingerprints of climate processes? Also interested in looking at more short-term time intervals, as is being done by colleague Joe McInerney at NCAR, and looking at whether the changes you see in hydrogen and other species more follow the more monotonic increases of carbon dioxide or the more variable temporal increases in methane. To connect, I'll just say a word or two about how we are planning to connect the models and the observations, and then move on to the conclusions. So to connect the models and observations, we use forward modeling. And a forward model can be used in multiple ways. One is to retrieve geophysical parameters from emission observations, but it can also be used to make comparisons between observations and model predictions. So what we're using the first studies we used an empirical model of the middle and upper atmosphere, the MSIS model, and we're using a model, forward model developed by James Bishop. I'll just show one result here and then move on to the conclusions because of the time. But what we did is we put the MSIS model. MSIS model was determined provide the hydrogen profile in the the global resonance radiative transfer code. That code then predicted intensities that would be observed from the ground. And these are solar minimum observations, solar maximum observations, modeled solar minimum observations, modeled solar maximum observations. So that were modeled with a forward model. So what we can see here is that the general trend, the solar cycle trend, is consistent in the modeling and in the observations. However, there is a discrepancy in the total intensity. Okay, so now I just wanted to move on to the future work and conclusions. So some of the questions that we're interested in addressing are how did the predicted response of thermospheric hydrogen to greenhouse gases and the solar cycle compare with observations, and more observations are needed to address this issue. Which hydrogen-containing species are most sensitive to greenhouse gases? Is there a particular altitude in which they're most sensitive? Might there be a particular geographic point also at which they're most sensitive and can be perhaps better used as diagnostics? Which mechanisms are associated with these processes? To what extent might hydrogen and other hydrogen-containing species provide additional vertical footprints to help better understand climate processes? And so the way we're planning to try to address these questions are to new observations that we spoke about earlier from the northern and southern hemisphere, comparison of observations taken of other hydrogen-containing species, looking to see whether patterns are similar. How are they similar? How do they differ? Additional modeling studies with the WACM-X model to understand connections to greenhouse gases, stratospheric hydrogen, and to other hydrogen-containing constituents. Use of forward modeling to compare the observations in the model simulation. I'm also very interested in education and outreach relating to climate science and mitigation, especially given the very short time frames that we have for making significant changes to avert these horrible climate impacts. Also, as Michael mentioned, I'm involved in the Physics Learning Center. I'd be happy to talk about that. And we've had wonderful participants and tutors, peer mentor tutors from atmospheric sciences, and would love to have more. Also, possible application of spatial heterodyne spectroscopy with the proposal that Brad submitted to use this technology to apply to greenhouse gas measurement studies, the troposphere. So some conclusions are that whole atmosphere climate impacts extend through the uppermost regions of the atmosphere, with in the thermosphere, the temperature observed and temperature predictions and observations of a higher magnitude than below, at altitudes below. That we see a statistically significant solar cycle variation in the observations. The suggestion of an increase between two solar cycles, measurements made between two solar cycles, the 1990-91 solar max and the 2000-2001 solar max. That's surprising because it's counter to what we would have expected given our current understanding of solar cycle impact on the emissions. And likely of higher magnitude than would be predicted by simulations due to greenhouse gases. But the caveat is that it's a limited data set and further data are needed. And model simulations indicate that both carbon dioxide and methane carbon dioxide cooling and methane increases to the source species for hydrogen are both predicted to lead to increases in hydrogen at the highest altitudes. I also wanted to mention in closing that a part of the middle and upper atmospheric community, a subset of us, are trying to look at like how the work that we're doing can better contribute to understanding of climate change processes. How can we better work with the troposphere community? Some of the questions are, can some of the techniques we're using, like the spatial heterodyne spectrometer, and some of the data sets also provide tropospheric information. Can the processes in the middle and upper atmosphere, can any the understanding of those processes help with understanding the lower altitude? Also try to understand better ways of assessing uncertainties using some of the frameworks from the climate assessments, how we can potentially contribute to climate assessment processes, strategies for communicating climate science, and then practices for our meetings. So certainly greatly welcome your feedback. And again, thank you so much for the opportunity to be here. I am here afterwards for questions if you have them. I also kept my schedule pretty free tomorrow, which is not always free, but I always am happy to meet. But tomorrow is pretty free, and then also I'm here on campus, so certainly if you have more questions, very happy to meet you all. And thank you again. Sorry, I'm much late, 4:30.
We have some time for a few questions.
So one of the things that you showed here is that with the increased CO2, you end up with more hydrogen in the thermosphere.
Yeah.
And what I'm worried about, I guess, is the reductive properties of the Earth system as a whole. And if you look back at like 3 billion years ago when carbon dioxide was maybe 10 bars in the atmosphere, would that imply that in those high CO2 times that there would be more loss of hydrogen in general from the Earth system, or is the increase in hydrogen aloft due more to more lofting of hydrogen-containing species from below, so more like just a more source?
Right. Well, that's a great question, which I haven't thought about, but it's a great question to think about. But I can answer the second part, that the model simulations are indicating that it's likely that there is a predicted impact due both to methane changes to the source species and water vapor that fans at the tropopause, but also carbon dioxide cooling. And the cooling mechanism seems to be consistent with higher densities also predicted during and observed during or retrieved from observations during solar minimum cooler time. Also the cooler dawn period showing higher emission intensities. And the mechanism for why that is still why the cooling is leading to higher density is still a topic of investigation, especially by some colleagues at NCAR, but it may be consistent with a redistribution of hydrogen in the atmosphere, and also with complex dynamics, including diffusion. There's a paper by Li Chen that just came out in 2018 that is starting to address that issue.
Given that, at those altitudes, you have a stratification due to species, is it
That's
possible
right.
that the cooling just means that you're seeing an area that is traditionally more hydrogen? Is that the interpretation, or?
I think it's actually that there's more hydrogen associated with various processes related to cooling, and all the others, or many of the other species, are decreasing in density up there, but hydrogen is increasing, so it's counter to the other. Yeah, thanks for the question, though. Yeah.
Your discrepancy between the previous and the most recent solar max.
And it's actually not the most recent.
Oh,
We wish we had data,
those
but
two,
the solar
but between those two?
Yeah.
So the first one was, there was El Chichong and there was Pinatubo.
Oh,
You
yeah.
accounted for, it sounds
Right.
like you accounted for tropospheric scattering, but
You know, right.
what about stratospheric aerosols?
Right. Actually, our colleague Ariana, she initiated a study looking at, she's working on, she's a student working with Nifan and me, she's working on looking at impacts of volcanoes on hydrogen emissions. So that might help to explain it.
It wouldn't even just be emissions, just more scattering.
More scattering. Also, I think what she seems more scattering for me. Say a little bit more about the,
So, you've got more aerosols and you're looking and invisible, so you're going to see, you would see less with stratospheric aerosol loading from the surface than you would now or more recently where it's very pristine in the stratosphere.
Would you expect, do you think that would change the background intensity?
I don't know, I just know that,
Right.
you have two, it was sort of around El Chichong and two.
It's something we should really look at, so thank you for that. And I have an idea I wanted to ask you about later too, about how we might look at that, yes. So we have not yet. Thank you for that. But I think some other studies have, for other parameters. Yeah, John, thank you.
I'm trying to envision how the distributions of hydrogen, greenhouse gases, what they look like. and how they interact with each other, and
Oh.
what they look like in the vertical. Are they mixing between remote
Okay,
vertical
right.
altitudes? I mean, is there diffusion or convective mixing or dynamic mixing?
Right.
What process go on? So they,
And then there's conversion
Oh.
too from
just photochemical conversion.
photochemical conversion, but we are interested in looking at whether there's similar patterns, like in terms of where the whether there might be similar at least I'm interested in looking in the modeling and see whether you see similar patterns of where if there are locations in which you see more of one particular species at a particular altitude, how far up does that pattern continue?
Yeah, I'm kind of wondering if there's a synoptics of the
Yeah.
total atmosphere
Yeah.
that goes on to
Right.
actually influence a little bit some of the changes you see.
Yeah, that there is.